बाल बिल ठीक कर ले भाई। यू आर नॉट ऑडिबल। हेलो। साउंड साउंड। साउंड विपिन। साउंड। हेलो। साउंड साउंड, तेरा साउंड काम नहीं कर रहा है। नहीं कर रहा है। नहीं, कुछ बोल। एक सेकंड। बोल अभी कुछ। कुछ बोल। नहीं, आवाज नहीं आ रहा है कुछ भी। एयरपोर्ट से मत कनेक्ट कनेक्ट कर। एयरपोर्ट से सही से नहीं हो रहा। अभी बोल कुछ।
हेलो।
हाँ, अभी आ रहा है आवाज। एयरपोर्ट से नहीं हो रहा है काम।
मतलब एयरपोर्ट से क्यों नहीं होता?
पता नहीं क्यों। अभी आ रहा है ठीक है। अभी बोल कुछ। नहीं, अभी नहीं आ रहा है, नहीं आ रहा है। नहीं। अभी बोल। नहीं आ रहा है।
हेलो। नाउ?
हाँ, अभी आ रहा है, अभी आ रहा है।
ओके। सो
क्या हुआ
नाउ
था? या नो, यूर ऑडिबल।
I'm audible now, right? So hi, welcome everyone to Waterloo ECS webinar series. Everything is fine, right?
या एवरीथिंग इज गुड।
Okay, let me share the screen then. Can you see my screen?
यस, आई कैन सी योर स्क्रीन।
S- So is this upper bar is also visible, or is everything okay?
Everything is visible. I think upper bar is not visible. In terms like everything, the poster is visible now.
Poster is visible, okay.
Yeah.
But and one more thing, Kiran, can
Yeah.
you also unmute and mute yourself?
Mute, unmute. Yeah.
You can, right?
I can mute and unmute myself. You can do it as well, right?
I
Because
don't
you
know.
are host.
Yeah, I can.
You can unmute me, I guess.
Okay, let me check. Okay, so
Yeah.
oh, sec. Okay,
Good
you're muted
morning.
now, right?
You muted me. Yeah.
Yeah. So now, yeah.
Okay. So if you unmute me, I have the like I have like they gave me a notification that the host is trying to unmute you, so I have option to unmute me or not. You can't unmute me.
Oh, I
Up to
see.
me.
So
So you can
now, check it now. He's unmuted now.
you can muted me. You can mute me, but to unmute me, it's my choice.
Okay. Okay,
Yeah.
sounds good. Okay.
Yeah.
Yep, same happened with me.
Oh, same. Okay. So yeah, I think the mute unmute button is also like working fine.
Yeah, I think it makes sense because like if someone is talking during the thing, you can mute them, but like you shouldn't be able to just like randomly open their mic.
Yeah, yeah, makes sense. How about the Okay, so I'm not pretty familiar with this Zoom. Where is the chat section for that? Like, do you guys know where I can find the chat?
It should be at the wait. Uh, I think it's at the top, like next to the participants list or something like that. Yeah, just send a message to
Oh,
kind
okay.
of give you a notification.
Oh yeah, it's here. It's here. Yeah, I got it. Thanks.
Also, I'll send you a message with the seminar code, so like 15 minutes before the end. Just like copy paste the message because I'm not sure if I'll be able to at that time. Like I'll still be listening in, but I might be a bit busy. So
Okay,
if you could do that, that would be super.
sure, perfect. You can just text me on that group. I can just copy that from there. Hi, Professor McDowell. Just wanted to cross-check. Can you unmute yourself? No.
Great. That works. Can you hear me okay?
I can hear you.
Great.
So, okay, it's almost time. We can start now. So hi, welcome everyone to the Waterloo ECS Electrochemical Society webinar series on interface matters, the role of interfaces in solid-state batteries. Myself, Vipin, I'm a third-year PhD student and a vice president of the Waterloo ECS student chapter. So today we are really excited and pleased to invite Professor Matthew McDowell from Georgia Tech. He's an associate professor with appointment in the Woodruff School of Mechanical Engineering and the School of Material Science and Engineering. He received his PhD from Stanford University in 2013 and was a postdoc at Caltech until 2015. He received numerous awards, just to name a few: NASA Earlier Career Faculty Award, Sloan Research Fellowship, Georgia Tech Outstanding Achievement Earlier Career Award, and many more. And today he will be speaking on understanding the evolution of electrodes and interfaces in solid-state batteries. Professor McDowell, we look forward to your talk and thank you for your time.
Great. Thank you. Let me go ahead and share my screen here. Okay. Well, yes, thank you for the invitation. Much appreciated. Quite an honor. One of my current postdocs, actually, Pinar Alsak, did her PhD at Waterloo, graduated about 1.5 years ago now. So it's good crosstalk between the two different institutions. She's working on solid-state batteries now. So I'll tell you about my group's research today on solid-state batteries, and in particular on characterizing some of the degradation modes that occur in solid-state batteries and at their interfaces. So here's an overview of my research group. We have quite a bit of activity on different battery systems. About half my group is working on solid-state batteries, and then we're also working on a number of other energy storage systems. These include new sustainable materials for batteries, as well as low-temperature battery chemistries, and some projects on larger scale storage systems for grid storage. One of the things that we're known for, one of the things we do in a lot of these different projects is we develop operando and in situ techniques to experimentally characterize the evolution of battery materials. I'll show you some of our work there. So probably a lot of the folks on the call are pretty familiar already with solid-state batteries, but if you're not, the reason why many people are interested in them is because they could have higher energy density and improved safety compared to lithium-ion batteries. So this is a schematic of a conventional lithium-ion battery where you have a graphite anode, a metal oxide cathode, and then liquid electrolyte throughout the whole structure. So moving to a solid-state battery, you basically just replace that liquid with a solid material that still conducts ions, has a high ionic conductivity. And this could enable you to use new electrode materials with higher capacity, like a lithium metal anode. And if you can do that, you'll boost the energy metrics of the cell. So this shows basically about a 40% specific energy boost and a 70% energy density boost. And you'll potentially get higher safety as well, or improved safety, because of the lack of a flammable liquid electrolyte. And so these sorts of energy metrics are important for electric mobility applications, both electric vehicles with longer ranges, as well as these newer eVTOL applications, electric vertical takeoff and landing aircraft. The first manufacturing facility for this Archer company is near Atlanta, actually, in Georgia, in the US. All right, so solid-state batteries could be awesome, but there are a lot of very scientifically interesting problems and technically challenging problems associated with having all solid-solid interfaces in an electrochemical cell. Many of these are associated with chemomechanics and the interaction of electrochemistry and mechanical stress in these batteries. And one of our goals as a group over the years has been to visualize and understand some of the fundamental mechanisms that are associated with charge and discharge of solid-state batteries, and link these to chemomechanical interactions within the cell, as you'll see in the talk. So I've organized this today into 3 different sections. The first 2 sections will focus on lithium metal anodes and solid-state batteries. The first section is just kind of an overview of some of the things that we've learned over the years about degradation methods or degradation mechanisms. And the second section here is specifically focused on what we call anode-free solid-state cells, where you start with no lithium at the anode. The final topic will be focused not on lithium metal anodes, but instead on alloy-based anodes, alloys like silicon and aluminum, which also have high capacity for solid-state batteries and show very intriguing behavior when you compare them to their behavior in liquid cell batteries. So these are the topics all focused on anodes and interfaces, but just different types of anodes. Okay, so let's jump into it here. The overall field over the last, I guess 10 years now has learned a lot about how lithium metal behaves in solid state batteries. There's still more to learn actually, but 10 years ago, there was really not much known at all. There are major challenges of using lithium metal, and there are two specific things that limit performance. The first thing is the fact that lithium grows dendritically or in a filamentary fashion through solid electrolyte materials. So even though lithium is very soft and has a low yield strength, it can penetrate very high stiffness ceramics, it can penetrate polymers, and it grows through these materials to short circuit the cell, which kills your cell. Bad situation. So this is a major problem. The other major problem occurs when you're discharging the battery instead of charging the battery. And it's the fact that when you have a solid-solid interface, lithium metal, as you strip it, as you oxidize lithium and remove the ions through the solid electrolyte, it has a tendency to form voids and pores at the interface. And this is also really bad. It causes a higher impedance. It causes current concentrations at regions that still contact, like right here. And then when you try to recharge the cell, you grow lithium at these contacting regions, and it causes very high local current densities, which induces filament formation. So these two processes are related. The void formation and filament formation, charge and discharge, they're related, and they kind of exacerbate each other, and then the cell fails. So this has been a major problem, and just understanding these processes has been a big focus of a lot of solid-state battery research. So what have we done in this area? A few years ago now, we focused on investigations of contact loss and these materials. It's a void formation and contact loss at the interface between lithium and a solid electrolyte. And we did some visualization of this, which I'll show you in a second. But this was inspired by some really key electrochemical measurements, electrochemical observations by a number of different groups 4 years ago or so now, 4 or 5 years ago. So Peter Bruce's group, Jeff Sakamoto's group, and Jürgen Janik's group all came out with papers around the same time that basically showed electrochemical evidence for the fact that you can lose contact at a lithium solid electrolyte interface during stripping. And this fundamentally, this is a fairly simple process, I guess, intuitively, but in reality, it could be much more complicated. But the idea is that if you're stripping lithium too quickly, if your migration of lithium through the solid electrolyte is faster than either self-diffusion or mechanical deformation of the lithium electrode itself can fill in these vacancies that are forming, then you by necessity will have vacancies that coalesce to form voids at the interface. And again, these voids represent a loss of contact and cause much higher impedance and cell failure eventually. So this was predicted based on these electrochemical observations, but what we wanted to do was to see if we could visualize this process using operando characterization. And so we selected operando synchrotron tomography at a beamline, X-ray tomography, to try to understand this process in more detail. So I'll give you a little bit of information here, since I'll show some other results from tomography experiments throughout the talk. So to do these sorts of experiments, we make these specialized custom cells shown here on the left. This is one type we make. They're very small. The diameter of the cell is about 2 millimeters. And it allows us to apply a stack pressure to the cell and seal the cell so that it can be operated in air. And the size is specified so that X-rays can penetrate it and be used for imaging. So these particular experiments we do at Argonne National Lab at the Advanced Photon Source Synchrotron. We take these sorts of cells, we make them there, and then we charge and discharge. This is some electrochemical data shown on the right. And about every 15 minutes or so, we take a 3-dimensional X-ray scan of the cell. So the way that tomography works is you take a bunch of 2-dimensional projection images, and then you use an algorithm to recombine those, reconstruct those into a 3-dimensional data set that contains all the image information in your material or your cell. And for these experiments, we achieved about a 1.7 micron voxel size, a 3D pixel. So we're seeing things, the resolutions on that order, and we have scans every 15 minutes. So what does this data look like? So now this is just a 2D cross-section, a reconstruction of the interface. Here we're looking at lithium in contact with a solid electrolyte. This solid electrolyte is a sulfide material. It's lithium tin phosphorus sulfide, one that is not stable in contact with lithium, actually. And so we'll see that in a second. But as we strip lithium, this is a portion of the interface before any sort of electrochemistry, just the pristine interface. You can see there's fairly good contact. After we've oxidized and stripped lithium, the lithium electrode has shrunk a lot. It's decreased in thickness, but also you form these dark splotches at the interface. These are voids. We know these are voids because their intensity is lower than anywhere else in the cell. It's just a lack of material. And we can map out these voids by doing image segmentation across the entire 3D structure of the cell and classifying different voxels into different phases based on their intensity and proximity and other factors. Here we see that we can see the interface intensity is very low when the voids form. So this is now a 3D view of the segmented data set from these X-ray tomography experiments. Here's a pristine portion of the interface. We're looking at the solid electrolyte here, and lithium is above this solid electrolyte. It's transparent in these views. The purple voxels are voids or lack of contact between the lithium and the electrolyte. So as we start, there's some voids. As we strip the full cell here, you see that at the end of the stripping experiment, there's quite a lot of voids that are present. There's a lot of purple that is covering the interface. So 3D views are cool, but actually I find it more useful to look at these projection images. So these are what we call contact area maps. We're looking at a projected view of the whole interface, and the yellow pixels are pixels of contact. So when we lose the yellow, it means we're losing contact. The black pixels are lost contact at that position. So you can see as we strip the lithium here in these maps, we are losing a lot of the contacting area, and we're forming contacting regions that are isolated and relatively small. And this is associated with the electrochemistry up here. You can see this yellow curve here is this interface. And as we strip towards the end of stripping, we lose a lot of contact area on this interface. So we can quantify this with these experiments. So why is this important? We figured out all the different contacting areas, and we worked with a group at Purdue, Partha Mukherjee's group, to do some modeling here. And basically, you cannot predict the overpotential that we measure if you just take into account the overall area of contact loss. You have to take into account the distribution of contact and the size of these contacting regions, because when you do that, you see that there's these current constrictions that cause very high impedance, much higher than you expect with just the raw contact area. These current constrictions are a problem. They can cause filaments to form when you charge the cell. And this is the first time that anyone had measured these sorts of contact evolutions in these batteries. So this can be applied to any sort of solid state battery chemistry. It's important to understand how contact evolves during stripping. Okay, so that's contact loss, very big problem in solid state batteries. There's another thing that I'll mention that's kind of related to this, and this is the formation of an interface at solid state electrolyte interfaces. So if you're working in the battery area, you're probably familiar with this idea of a solid electrolyte interface, SEI. This is a really important aspect of commercial lithium-ion batteries. There's an SEI that forms on the anode. It turns out something similar happens in solid state batteries. Various solid electrolyte materials, like the one shown here, have different stabilities in contact with lithium and other electrodes. And many of them are unstable at low potentials like that of lithium metal. This particular material, lithium tin phosphorus sulfide, is really quite unstable with lithium. You can see here in this video, this is an X-ray video now over about 10 hours of an experiment. And what you're seeing is this intermediate contrast phase that's forming at the bottom and the top interfaces where lithium's present. This phase is actually interphase. It's an interface layer that's growing into the solid electrolyte. So it's growing dynamically, and it's really quite thick. So this is not good for a real battery. You'd never want this to happen in a real battery. But the point here is that you can quantify the growth of this phase with this sort of technique as long as it's fairly large. So we did that in this paper here, these experiments, so we can see that the interface is growing linearly with time, actually, in this case, as we're applying a current. So this represents an interface-controlled two-phase type reaction for this interface growth, which was expected. We've also done some other work in my group. I've only talked about X-ray imaging so far, but this is a different type of experiment. And this is really the only slide I'll show in this. So maybe a little quick here, but this is where we're using TEM, so much higher resolution imaging in an electron microscope to understand what's happening during this interphase formation. This is with a different solid electrolyte material. This is an oxide material, a NASICON type lithium ion conductor, LAGP. Long story short, what we see in these experiments, we actually react the LAGP with lithium in a microscope, and we see that there's this volume expansion and an amorphization process. So the interphase can form and it involves a reaction of the solid electrolyte with lithium, and it can significantly change the structure and properties of this material, as shown here. Another consequence of interphase formation, and this is back to X-ray imaging, and again in the same solid electrolyte material, is that the interphase process, interphase formation process itself can cause mechanical damage. So this is, again, back to this idea of chemomechanics. So this is an X-ray tomography experiment where we ran a symmetric cell with an oxide solid electrolyte for many hours, charge and discharge. And over time, we see that this interphase builds up and forms. It grows on the surface between the lithium and the solid electrolyte. And there's this volume expansion associated with the interphase formation. In this case, the interphase is quite thick, tens of microns or thicker. And this volume expansion induces stress in the ceramic and actually causes the ceramic itself to fracture. So these images here just show that these cracks are forming in this ceramic pellet. And the bottom row of images is the segmented fracture pattern. So this is kind of an important detail here, but often we just think of the interphase in terms of its transport properties or how it influences the stability of the interface, but it can also have a mechanics effect, which is what this emphasizes. And this is a video of this over the long experiment, 40-hour experiment, where these cracks are forming in this pellet. And we found by quantifying how this relates to the impedance starts increasing when you have these cracks growing, not when the interphase is forming. So the cracks are really what are detrimental for the impedance. All right, I'll skip through this here. All right, the last thing I'll say about these fundamental lithium degradation modes is related to lithium filament growth. And so we've talked about voids that are forming at the interface. We've talked about chemical instabilities and interphase formation. So this last part is lithium filament growth or lithium dendrite growth. There's been a lot of work done on trying to understand lithium filament growth in solid state batteries. It's a very challenging and complex process to understand. We have some work on this. This is just an X-ray CT video that's on repeat showing filaments growing through a solid electrolyte. I think that the general state of understanding in the field is that this is truly a mechanics process. There's stresses that are evolved near the crack tip due to lithium growth. Lithium is under high compressive stresses in these cracks, and it basically forces itself and causes these cracks to propagate through the solid electrolyte. We have a paper that was published a year and a half ago or so, focused on understanding lithium filament growth. And one of the things that we found that was kind of interesting, this is especially for the experts in the audience, if you have a normal sulfide type solid electrolyte, like an argurodite Li6 PS5 Cl material, usually people make these into batteries by cold pressing them, and there's some density associated with the cold pressed body, usually around 90% or so. It can be a little better, but they're somewhat porous. They have high conductivity, but they're somewhat porous. And when you do these sorts of CCD, critical current density type experiments, you can get some value for the current density. But really, when you push lithium in one direction across a symmetric cell like this, what you find is, regardless of the current density, you will always eventually form a short circuit. We tested dozens and dozens of these cells, and we always found a short circuit. You might have to pass quite a lot of lithium. In this case, there's over 100 microns of lithium being passed, but you will always have a short circuit. So that's a problem. this is just a map that's kind of showing that these short circuits are pervasive, and they always form these sorts of ceramic electrolytes with relatively low density. And we think this is related to growth through some of the pores in the solid electrolyte, or at least exacerbates the fracture process. But this just kind of illustrates that these dendrites and filaments are quite difficult to prevent unless you can have careful processing of these materials. So that's the last challenge I'll mention, and that gives an overview in the first section here on the various mechanisms that control the behavior of lithium. So we will move on to the next topic. This is related to the first section, but it's specifically focused on lithium interfaces in what we call anode-free solid-state battery cells. So what is an anode-free solid-state battery? So normally, well, in many testing scenarios, what you see in the literature is that a battery will be constructed with a cathode, like an NMC type cathode, some sort of separator that's usually much thicker than 20 microns, and then a lithium foil. And usually the foils are really quite thick, that people test them in a lab scale on the order of hundreds of microns. But for a commercialization setting, you'd expect thicknesses on the order of this left image here, where you have a 25 micron or so thick lithium foil, and these other thicknesses are associated with what you can expect to get this energy density with. So this is a normal excess lithium cell, we call it. And we know that these sorts of cells are limited by the critical current density during plating that governs dendrite growth, and then the stripping critical current density. If we go higher than that, we can cause voids to form. So the question that we asked when we started this work is, if we move to a scenario where we have an anode-free cell, what this means is it's basically just you take the lithium foil out of the anode side. So you have no active material at the anode to start with. And on the first charge of your cell, you move your lithium ions down to the anode and you reduce them and plate out lithium metal on a current collector. The reason why you want to do this is because it can result in higher energy density. You have minimal material at the anode, and so it's commercially very attractive. So the question we asked is, all right, if we move from this scenario to this scenario, we're just getting rid of lithium. How does this affect behavior, and what sort of limiting mechanisms apply to these sorts of cells and solid-state batteries? And we didn't quite know what to expect, to be honest, because when we first started this, because there had not been a lot of studies published in the literature, even on just anode-free plating of lithium onto current collectors, especially with these sulfide type solid electrolytes, as well as oxides. And so we were kind of puzzled a little bit why this was the case. What we found is that it's really difficult to make these cells, actually. They're very tricky to handle, and you have to have everything very precisely controlled in terms of the uniformity of the different layers, the height differences on the current collectors and the rods here in these sorts of cells, then also the pressure distribution across the cells. So we're running these at 15 megapascal stack pressure. But basically what we found is, by a series of optimization steps and cell design steps, we were able to get very good performance in terms of lithium deposition. Here I'm showing at a moderate current density, 0.5 milliamp per centimeter squared, we can deposit a lot of lithium onto a copper current collector. Here it's over 100 microns. And when we go to higher current densities, we can still deposit quite a bit of lithium, but we eventually run into short circuiting issues. So basically, if you are very careful about your cell construction, you can get good lithium deposition performance in these sorts of cells. So that's good. That's a good start. We mapped out some of the details of this deposited lithium with synchrotron tomography. You can see generally when we deposit lithium, it's not that uniform. This is a height map of lithium metal across 800 by 800 microns of the interface. And you can see some regions are 60 microns thick, other regions are 15, 20 microns thick. So there is some variation in the thickness across the interface in these sorts of lab cells. And it's more uniform at lower current densities. So what's the problem then? So we can plate lithium, we can characterize it. So what we see is when we try to cycle these anode-free cells, either in half cells or full cells, a lot of data here, sorry. What we see is that the anode-free cells short circuit much more rapidly than excess lithium cells. So this is a half cell showing that it's short circuiting on the third cycle. Generally, over many tests, we see it always short circuits before the fifth cycle. And if we do the same test in kind of a symmetric cell with lithium on both sides, we can cycle hundreds of times without short circuiting reliably. So clearly there's something different that's happening. Same thing in full cells, where here we're short circuiting within the first 10 cycles. That's very common. Whereas with excess lithium full cells, we can cycle over 100 times without short circuiting. So something different is happening here. So what we think is happening is shown in this schematic. Basically, the difference between a lithium excess cell and an anode-free cell is that at the end of stripping, you're trying to get rid of all the lithium that's present in the anode-free cell. You want to remove all of it from the interface. And so if you have a situation, which we think is pretty much always the case, where there's somewhat non-uniform lithium across the interface, like this, when we get towards the end of stripping, that means that we're going to have some regions that are fully stripped of lithium and contacting between the current collector and the solid electrolyte, and other regions where there's still lithium remaining. And this is a problem. This is where we think this problem is arising, because now what we're doing as we continue to strip this lithium that is present here at this island, we're forcing the current to go towards these remaining islands. This causes high local current densities, which necessarily causes voids to eventually form at these remaining islands. So you'll have some voiding at these remaining regions. Then when you reverse the current and grow lithium, these voids again cause the current to be concentrated, and that's where you may grow filaments at the edges of these voided regions. So basically it's this kind of necessity of not having completely atomically uniform stripped lithium that will cause these filaments to grow. So there's some electrochemical evidence for this as well, and modeling evidence. This is modeling from a colleagues group who's now at University of Oxford in the UK, showing that voiding can happen in this phase field model if you have this kind of protrusion, or this simulates a lithium island. So this is a problem. One of the things we've investigated to try to solve this problem is the benefits or mechanisms of alloy layers. So this is a similar scenario here. If you look at this middle schematic, we're now testing a half cell with a copper current collector. Instead of just bare copper, we're depositing 100 nanometers of either silver or gold. So there's been a lot of work in literature focused on silver in particular, showing that it, in various contexts, either in composite electrodes or other types of interfaces, it can behave pretty well. And what we wanted to do here was understand why this is happening. So we showed here that if you just have these thin layers deposited on copper, you can significantly improve the Coulomb efficiency and the cyclability of these anode-free cells. 30 to 40 cycles without short circuiting, whereas again, without these layers, it's just a few cycles. So they're improving performance. We wanted to figure out why. So one of the things we noticed that was interesting, if you deposit lithium on these various interfaces with these silver-coated current collectors, gold-coated current collectors, or just bare copper, the morphology and the structure is very different. So with bare copper, the lithium region is shown here. These are plasma fib images. So we've cut into the cells after extracting them, after depositing lithium. You can see that the lithium, this darker region, is quite non-uniform. There are pores and voids present at the interface, and some of the lithium is actually grown into the solid electrolyte pores. So this is preparing to short circuit, basically. When we have silver-coated copper, the lithium is much more uniform overall. That's important. There's also some evidence of silver present. Silver partially dissolves into the lithium because it forms a solid solution. The gold-coated one is quite interesting, though. What happens is the lithium deposits, it alloys with the gold to form a lithium gold alloy, and actually this gold film then breaks up into particles, and you can actually see these lithium gold alloy particles at both interfaces after lithium deposition. So there's a very dynamic interlayer, a very dynamic interface, actually. Lithium reacts with gold, the gold particles break up, and part of that gold is then carried across the interface as lithium grows. So when you strip, the gold comes back and lithium is removed from it, and presumably it comes back to the interface and sits there as well. So these are just some X-ray characterization now showing, just like the fib, we see that when we have a silver present, that the deposited lithium is much more uniform in thickness across the interface. Okay, so why is this happening? Well, or actually, before I get there, this is one more piece of evidence, and this is a busy slide. I apologize, but this is electrochemical impedance spectroscopy. It's pretty important. We did a lot of EIS measurements for this paper, and this is just a small portion of them. But what this shows is basically near the end of stripping, when you have bare copper, you get this this distinctive spectral shape where you have this intermediate frequency region that grows, and we think this impedance spectrum feature is associated with void growth near the end of stripping. When you have silver and gold films, you don't see this sort of feature, and in fact, the impedance spectra remain fairly similar with cycling, which is a mark that that there's good contact at the interface. So basically, we think that both there's two factors. These inner layers are allowing for nucleation and growth that occurs in a different way, and there's much more uniform lithium growth across the interface, which is useful. The inner layers also help to retain contact at the very end of stripping, which allows for much better cycling and prevents, at least initially prevents, filament formation. And there's a model here that was also developed to explore this in more detail. There's some evidence that there's potentially release of lithium from these layers as well, which can help mitigate some of the voiding issues. This is we're doing some more work on this as well currently. All right, good. Well, I think I have maybe 12 minutes or so left, and then we have some time for questions. So I talked about anode-free cells, talked about lithium metal anodes. This last section, I will discuss some of our work on alloy-based anodes for solid-state batteries. I'm very excited about this part. This is an area that has grown a lot in my group the last few years. There's some really interesting prospects for alloy-based anodes in solid-state cells, and I'll explain why here. So alloy anodes, examples are silicon, tin, aluminum. These are materials that alloy with large amounts of lithium to form new phases, and they have high specific capacity. So silicon has been investigated, of course, for many, many years for lithium-ion batteries. There are commercial lithium-ion batteries that have silicon with liquid electrolytes. Usually there's very complicated particulate structures that are necessary to minimize SEI formation in liquid electrolytes with these materials. But this is continuing to be commercialized and improved for commercial cells. But for solid-state batteries, these are of interest because actually silicon and aluminum and tin and other alloys, they have similar energy densities to lithium metal solid-state batteries if you do the comparison. So you can see that, especially when you have even one times excess lithium metal, the energy densities of these cells with alloys are very similar. This is a schematic of what a cell might look like. You have an NMC or other composite cathode, a solid separator, and then some alloy-based anode. And I'll tell you about some architectures for these in a second. So these alloy anodes, one of the distinctive things about them is that they undergo very large volume changes during lithium insertion and extraction. And this is because they have very high capacities. They form new phases that are very rich in lithium. And so we did a study a few years ago where we were measuring stress changes in solid-state battery cells with different alloy anode materials. These are data from this paper. We were exploring antimony, tin, and silicon. And these are electrochemical plots on the top in black where we're charging and discharging various cells. And then the red down here is real-time measurements of stress changes, stack pressure changes in these cells with the force sensor. And what you see is as you charge the battery and discharge the battery, there's a big increase by a few megapascals of the stress in the cell and then a decrease of the stress. And in general, these changes in stress are higher than in liquid cells because there's just a more confined environment in these solid-state batteries. There's a really good paper here from Jürgen Janik's group that goes into some details about how partial molar volume of lithium influences the stress evolution, and these types of materials are highly recommended. Good. So volume changes. These volume changes are associated with structural degradation and mechanical degradation in these materials. So understanding and controlling this is really important in solid-state environments. So one of the very interesting things about alloy anodes and solid-state batteries is that they have shown very good performance, actually. So this is from the same paper from my group where we take silicon microparticles and make composite electrodes with solid electrolytes, or sulfide-based solid electrolytes, and we cycle them in batteries, and we see decent cycling over 100 cycles, pretty good stability. And this was really quite surprising when we initially started this work 4 years ago, because if you do the same thing with these sorts of microparticles in liquid cells, you see really rapid capacity decay in a half cell. Really terrible performance. And this is because these particles break up into pieces and there's a lot of SEI that forms. So intrinsically, you can have the case where a solid-solid interface chemically is more stable than a solid-liquid interface when you're using these alloy materials. And this leads to improved cyclability. Of course, Professor Shirley Mung's group published a very nice paper in Science a few years ago where they showed very good cyclability for silicon-based solid-state batteries. Notably, all these are at high stack pressure. So this is, I think, 50 megapascals. This is 20 megapascals. One of the challenges is getting to low stack pressure. I'll talk about that as well. But in general, this initial work was quite intriguing, and it brings about the question of, can we develop alloy anodes and manage chemomechanical effects and enable their operation at low stack pressures for solid-state batteries. And one of the things we've focused on, is what about dense alloy anodes? So silicon composites are fine. You lose some energy density. Slurry cast silicon is good, but really what this brings to the fore is, you could potentially use metal foils directly as anodes in solid-state batteries. This would be highly advantageous because a metal foil that stores lithium is 100% a lithium storage material. There's no other composite structures. They're easy to manufacture. Especially aluminum-based materials are used widely and are low cost. And so we've been focusing on figuring out if we can use dense foil-based alloy anodes in solid-state batteries. And it's particularly those based on aluminum. Again, the energy metrics are appropriate and exciting for aluminum-based materials, similar to silicon-based materials. But if you're using a foil directly as an anode, you get rid of all the slurry coating that you need on the anode side. The slurry coating in battery manufacturing takes about half the energy required because you have to recycle the solvent. And so getting rid of slurry coating is highly advantageous. And so if we can just use the foil, we could potentially have high energy density and remove some of the manufacturing costs. So aluminum in particular as an alloy anode was originally looked at many decades ago. There's major SEI problems in liquids, but I'll show you in a second, we can overcome this in solid-state batteries. Beyond that, there's issues with mechanical degradation and trapping of lithium within the structure and the material itself. So we've been working on how to develop materials and composite microstructures that can overcome these issues. So in my group, we've been doing a lot of metallurgy recently, actually. We have equipment where we can do small-scale cold rolling and make all sorts of different alloys of materials. So in particular, we focused on these multi-phase aluminum materials. So we start with aluminum, we mix other materials like tin or indium or zinc into it, we heat it, we cool it, and then we can roll it out as a foil. And you can see that we can kind of define different sorts of microstructures. So here's a layered microstructure with tin and indium as a two-phase microstructure. Here's zinc, forms a particulate microstructure with an indium. And here's a solid solution. This is actually with gallium. So what we found is we've investigated these in solid-state batteries, and we found this particular material amongst a few other candidates to be quite interesting. So this is a material that's 95% aluminum and about 5% indium. When you do this, you make this alloy, you roll it out, you see that there's a completely phase-separated microstructure. There's no alloying, there's no compound formation. Indium, the lighter phase here, is dispersed as these layers within the aluminum structure. And this happens to be a very useful microstructure for batteries. And when you test these in battery cells, in solid-state battery cells, you see that this alloy, aluminum indium alloy, has much higher capacity and better cyclability than just the pure aluminum. And one of the most important things, it has a much higher initial coulomb efficiency as well. So the indium phase within this aluminum microstructure, it reacts with lithium, just like aluminum does. And it has very high transport characteristics, high diffusivity. And so the instead of trapping lithium like pure aluminum, the interspersed lithium indium phase allows for lithium to be removed from the structure more effectively and increases the initial coulomb efficiency. We've seen very good durability on these materials at relatively high stack pressures in solid-state batteries. This is 500 cycles with controlled capacity cycling. We also see that this two-phase microstructure improves the rate capabilities quite a bit as well. We can get up to 6 or 7 milliamps per centimeter squared in a lab scale cell without short circuiting. and retain some of the capacity as well. So this is a view of the microstructural evolution of these materials. This is the pristine layered material. After you lithiate, there's this big expansion of the foil because you've inserted a lot of lithium. And the important thing here is that the microstructure still remains intact. You see the layered phase, the lithium indium phase is still there. When we delithiate, we have contraction again, and the microstructure is still intact. So the persistence of this microstructure, we think, is important for cycling. We've explored this in more detail electrochemically. This is pretty interesting, this plot here, from an electrochemistry standpoint. I hope I don't lose some folks in the discussion, but we're almost done here, so just a little longer. But what we see here is, this is just a half cell test now, where we're using the galvanostatic intermittent titration technique, GIT, which is a electrochemical technique where we apply a current and then rest the cell for a certain amount of time and monitor the potential as we rest. So what you see basically is we're testing two different cells here. One has an aluminum indium electrode and one has pure aluminum. The pure aluminum has some overpotential. It's about 150 to 200 millivolt overpotential during the lithiation process, which is expected. The indium aluminum is interesting. So first, what happens is the indium within the foil reacts. That's this higher plateau here. So the indium completely transforms to lithium indium. But then during the aluminum lithiation down here, this blue part down here, it has a much lower overpotential, much lower than the pure aluminum. So the presence of the lithiated indium in the cell is significantly reducing the overpotential of the aluminum reaction. And this is, we think, because there's better transport of lithium, and there's a 3D network of the indium within the structure that allows for a lower overpotential during the aluminum reaction. So this is very useful for improving kinetics. All right, so overall, the distribution of the secondary phase, lithium indium phase within the structure is very useful for improving kinetics, improving coulomb efficiency, and improving cyclability. And we think that this sort of idea of microstructural engineering of anodes can be very useful, even working towards commercialization for solid state batteries. And I'll just skip through this. This is testing in liquid cells. It's quite bad in liquid cells because of SCI formation. So what we're doing now in this project is we're actually building larger pouch cells. So everything I showed you was small scale, kind of anvil type cells. We're doing dry processing of the separators and the cathodes, making larger pouch cells and testing them at low stack pressures, actually. So we've developed some interfacial coatings that allow us to go to less than 5 megapascal stack pressure and achieve good cycling as well. So this project is kind of moving towards demonstrations at a much larger scale that are necessary to be thinking about commercial applications. All right, great. So I will conclude here. I'll say that I think you saw in many of the projects that we're working on that there's this pretty important relationship between the chemistry and the mechanics of the materials that determines performance in solid state batteries. And I talked to you about lithium and anode-free lithium cells, but also I think these alloy-based anodes are really quite promising for solid state batteries. There's a bunch of companies working on silicon as well, but I think there's still some fundamental questions to answer. But I think over the next few years, there'll be a lot of progress here. Great. So I will thank my research group at Georgia Tech, shown here. A number of the folks in the group contributed: Jack, Stephanie, Lars, Sungkyun, Kong Chang, Kelsey, Eugene, and others. My collaborators, and then the funding primarily came from DOE, NASA, NSF, and a company for some of this work. So thank you very much for your attention. I'm happy to take any questions if there are questions or comments.
Thank you very much, Professor McDowell. It was a great talk. And thanks for sharing so many useful insights, especially the work on alloy anodes. So, so the floor is open for the questions. If anyone wants to ask anything, just please feel free to post them in the chat section. I think there are a few questions in the chat.
There are some questions in the chat. Should I go ahead and answer them, or maybe just let people ask them? How do you want me to do it?
Maybe you can just go ahead. That would even work.
Sure. Good. So there's a question about how an interface between the lithium and the salt electrolyte affects pore formation. This is a really good question. I didn't mention this. So what we've seen is that actually the interphase, which the formation of the interphase involves reacting the salt electrolyte with the lithium. And so some of the lithium disappears in the reaction into the, it doesn't disappear, it moves into the salt electrolyte. But that process can actually exacerbate void formation depending on how thick the interphase that forms, because you're using some of it to create this new phase. And generally, there's a volume contraction if you compare the partial molar volumes. So we've seen that this exacerbates pore formation. Good. Another question, the question about void formation again, but comparing half cells or symmetric cells to full cells. And so I showed some of the results from symmetric cells. In a symmetric cell, what you're doing is you're moving lithium from one side of the cell to the other side. And theoretically, if everything's working correctly, there should be no like overall volume changes in the cell because there's no changes in the chemistry at each anode or each electrode. So actually in a full cell, you have a lot of volume expansion at the anode during charge and then contraction during discharge. So, you know, depending on how you think about it, there may be some differences between full cells and anodes. We've seen actually, we've done experiments on both visualization experiments. We haven't seen major differences in terms of local void formation. It forms in both full cells and symmetric cells. I think there's some more work to be done on that because the kind of the crosstalk between the electrodes, I think, can be quite important for stresses. It hasn't been focused on as much in the literature. All right. There's a question about silicon being electrically insulating. Silicon, it is a semiconductor, but it's usually doped pretty heavily, and so it can be fairly electrically conductive. The electrical conductivity is not the limiting factor when you're using silicon electrodes in solid state cells. You can still charge and discharge at very high current densities. And then the last question I see on the chat is related to short circuiting. What is the best descriptor to determine short circuiting? Ooh, this could be a long discussion. I'll try to keep it short. So I briefly mentioned this idea of critical current density. Critical current density, it's an experimental measurement where you basically take a symmetric cell with a solid electrolyte between two lithium electrodes, and you pass current back and forth at increasingly higher current densities every cycle. And eventually you get to the point where you form a short circuit, and then whatever value of current density that happens, you say that's your critical current density. There's been a lot of controversy on this in the literature because actually, you know, it's very dependent on the specific cycling conditions and how the cells are made and things like this. So it's not, the critical current density is not some absolute number for a material. So we don't really know a single metric that describes filament growth and short circuiting. I showed briefly in just a slide or two how in our paper we showed that even at very low current densities, much lower than the critical current density, if you deposit lithium for long enough, you always form a short circuit. So there's also this kind of metric that's needed, the amount of lithium or the areal capacity that you're depositing. So there's not good consensus in the community about what sort of metrics that we need to really define this. There's a number of metrics you need to measure, but there's more work to be done there. Good. There's one, I guess there is one more chat question. Yes, this is a great question as well. Wonderful question. The question is, in a full cell, the negative electrode will be expanding and contracting. And so what are useful approaches to accommodate this volume change at the full cell level without having to apply high pressures? Great question. Yes, so this breathing of these sorts of cells is a really important aspect of how they work. If you talk to an OEM or a commercial battery manufacturer, there's really kind of a limited amount of breathing that they want in cells. And so there's been some new designs, I think, from some of the solid state companies that can accommodate some of these volume changes at a cell level. So there may be pretty large local volume changes, but at the cell level, there's less volume change. And so this I don't exactly know how they're doing it, but it probably encompasses some sort of like spring type mechanism that can apply some sort of constant low confining environment in the cell that results in some pressure without having to have any sort of bulky apparatus. But I'm not exactly sure about that. So I think there is some work to be done and some understanding to be had in terms of cell designs where you don't have to have a bulky apparatus, but you can have a constant pressure in a confined environment. And just for reference, For commercial applications, you need stack pressures that are on the order of a few megapascals or less, or ideally less than that. I think that's all the chat questions. Happy to take any other questions. Maybe it's hard to speak, I guess, because of the muting, but I don't know if there are any other questions.
I think so. This is it in the chat. I cannot see any other questions in the chat as well, but yeah. And I think
good. Well, thank you for the wonderful questions. Really, really good questions.
Yeah. So I think just to close things up now. So thanks again, once again, Professor McDowell. We appreciate your time, and also, I mean, it's great to see so many wonderful things that you are currently doing in your research group, and thank you very much, and have a good one.
Yeah, thank you. It was a pleasure, and thanks for the very good attendance. It's good to present our work in front of a good audience here. So thank you.
Have a good one, and thank you, audience, as well, for the time.
Thank you. Bye.
Bye.